Hey, looks like it's past time to start by a couple minutes, so let me get you guys started. Welcome back. I hope you've been working along real quickly or diligently on these chapters. I don't need to be one to tell you that they've been three very thorough, deep, maybe even challenging chapters here at the beginning. But let me just make a couple of announcements. The first one related to this class and the second one not related to this class. First one being where have we come from, where are we going, and in particular, when is the test? As you know, last time we took a little vote, overwhelming vote I might add, of what to do about the test day, and so we bumped it one more on the syllabus. So instead of having the test a week from today as originally written down on the syllabus and planned, it's the following Tuesday after that. So I believe that date came out to be October 2nd. So it's not this Tuesday but the following Tuesday, and it sounded like it worked out well for almost everyone, in the sense that it looks like math tests were next week there, and I know those can keep you busy too. So good. You'll have the math test next week, and then you'll have time there. Which then reminds me that not this weekend, but next weekend, or Don will do the review for you. So next week we'll put a little note up there, and decide on the day and the time and the place and all that. So stay abreast for that. Where have we done so far? Well, as you know, we've done 3 chapters. The point of these 3 chapters is really the physics part of our beginning here. We're about to kind of switch gears from that. We're about to enter about a couple of chapters here where it's more of the applied physics, where we build our little devices, we see what we can build, why we're learning what we are learning. But you learned, of course, about the electric field, you learned about electric potential, how they're connected, how you calculate them, how you would particularly calculate them for the different geometries. You'll see today that the different geometries play a different role, so there'll be advantage of doing it this way or doing it that way, and so what are the advantages and disadvantages, and of course that's where then your applied physics comes into play. How am I going to build these little devices? So there's announcement A. Announcement B, as I said, has nothing to do with the class, just a little combination of science, engineering, patriotism, history. But in case you haven't heard or paid much attention to the news, the very last space shuttle, the Endeavour, is flying piggyback right now here to California. It should be landing at Edwards Air Force Base real soon. All right. Tomorrow morning, it takes off. Nobody knows for sure where it's going. That's my disclaimer. But they have announced when it takes off, it will go over Sacramento, it will go over San Francisco, it will go over Monterey, it will go over Vandenberg, it will go over Malibu. Now, what is between Vandenberg and Malibu? We are, right? So, I'm hoping it'll be cruising down the coast. So keep your eyes open in that morning hours of after 9:30-ish. It's supposed to be in the LA airspace 10:30-ish. So if it comes by here, don't be surprised. There's a good chance. They don't want to really lay out the flight plan, because unfortunately somebody will try to shoot it down. So it's just the world we live in. Can you believe it or not here? So because we don't know where it's going to go, everything's kind of hanging on that. In my case, I'm actually going to drive to either Malibu or LAX or the Getty Museum or the Science Center Museum down in LA. I haven't decided, but somewhere down there. Maybe I'll go to Vandenberg. Probably not. I'll probably go that way, but I just don't want to miss it. I mean, I'm going to be bummed if I get a picture of it going over the Malibu pier when I could have got one going over the Santa Barbara pier, but we'll have to wait and see what happens. But I'll be more bummed if I'm in Santa Barbara and it doesn't come by here and I miss it altogether. So, yeah. And in fact, as a side note in all that, 3 weeks, whatever October 12th and 13th is when that leaves then LAX. It's going to land in LAX. It's going to then take 2 days to go 12 miles. LA traffic, right? But it's going to go across there to the Science Center when they get it all to its final destination. So that's the 12th and the 13th. And that's a Saturday. So again, I'm hoping on the 13th maybe to get down there and get it as it's cruising down the road there on their little tractor things. It's really kind of cool. It's like 4 big trucks they put, truck, and then I-beams across it, and so the shuttle's going to sit on it. And you know what a divided highway looks like, right? So they're going to close the road and put a truck on each side of the highway, so it's just going to span right over the center of the divider and go right down. So it should be cool. I guess the only negative thing is usually in the middle of those divided highways are trees. So yeah, they just cut down a bunch of trees so the shuttle can make a home there. But so if there's any tree huggers in there, I apologize there. But it's well worth it. They're going to replant them, all right? They'll grow back. Okay, and it's not old growth either. Okay, so just want to make that clear. All right, so where are we? We are on our way, hopefully, as I said, next series of chapters to take what we have learned about electric fields and apply them. And today's lecture is about that as we get into chapter 26 now. It's about what is a capacitor, and the capacitance to measure that capacitor. And so, for 2/3 of you, you already did the lab. The other 1/3 of you are going to do the lab this afternoon. But both today's lecture and the lab we did this week is exactly that. It's what is a capacitor? Oh, why would we care about it? So let me at least show you one reason why we would care about it and its usefulness. And then maybe next lecture on Tuesday, I'll show you a second one. And I think we'll see some other ones as the semester goes by here. But this is just to get that feel for it. And that much I got started. If you remember the last 15 minutes of class last time, I said, look, I wanted to kind of at least show you so the lab would go a little smoother for those of you on the Wednesday. I hope it did. But this would be a big capacitor. Not that it has a big capacitance, but its physical dimensions are big. And what I mean by that, a capacitor is just simply 2 metal plates. And so I'll maybe draw it something like this. Okay, and so we'll here's metal plate number 1. Here's metal plate number 2. I'll hook a wire to it. I'll hook a wire to this side. And what will happen if I went ahead and I forced electrons off of one and onto the other? Maybe I take them off of this one, so this would be plus, 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 plus. I put it on this one, minus, 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 minus. As we've done in previous chapters, that would set up an electric field, electric field, electric field, electric field between them. I guess the value of the electric field would be the surface charge density over the permittivity of free space. And so all of that we learned before, but this is what we call then a capacitor. It has a stored amount of charge, okay? And here's how we rate it, or here's how we measure it. Here's what we call its capacitance. Its capacitance is defined this way. How much charge do you get or need to move over in order for there to be a change of 1 volt? Okay? And so, as we kind of roughly put some numbers up here, I will grab a capacitor. Here happens to be a pretty significant size capacitor also. This one says right on it, it is 10 microfarads. So our units, if you remember from the last lecture, is the capacitance is measured in what's called a farad. Okay? Now, what that means then is it would take 10 microcoulombs of charge in order for there to change 1 volt on these metal plates that are buried down inside here. And if we were to open that up, it would look something like this. Or maybe, as I showed you last time, some of these capacitors that are rolled up in a cylinder. They are, again, two metal plates that when you lay them out, you will have metal plate number 1 and metal plate number 2. And of course, they need to be separated and have some kind of insulator between them. Obviously, if you did not have an insulator, and in this little picture, it's air. In this one, it's paper. But some kind of little insulator that will keep the charges from going from one plate back over to the other. And so that's the word we're going to call it's dielectric. For those of you who did the lab, you tried one or two of those. You put a piece of vinyl between here to see what would happen. You put a piece of paper between them to see what would happen. And then you guys in the lab today, that's what you'll do. In today's discussion, I'm not sure we'll get that far to dielectrics because we just want to get some of these general properties. As I said, just what is a capacitor? And so again, it is just a storage device. It stores charge. Let's see if I can demonstrate that. I happen to have two different capacitors I want to show you. This one is actually a very large capacitor. Now again, don't be deceived by its size. It has a lot of surface area and it is really close together, and as we'll see, that's part of our calculation. But this is actually 1 farad, okay? Which, remember, this was 10 microfarads. So this is 100,000 times bigger than this one. And obviously I don't mean in physical size, but in terms of storing charge it is. And so the reason I like this one in class is because I could then take a power supply and adjust it to roughly 5 volts. And those of you who did the lab, you saw this. Let's look at it again here. But I'll put it here at about 5 volts. And then I will hook one side of my power supply and the other side of my power supply to that capacitor. And so what's happening right now is charges are being forced from one plate over to another, and a little electric field is in there, okay? And so what I have, and like I said, one useful idea here of a capacitor is this is just a storage device. It now has stored charge. If I were to take this off, I now have charges. And I can hang on to it all day. Hey, what do you want to do with this? I don't know. Let's save it. Because who knows, in 12 hours it might get dark. So after 12 hours, I will plug it into my light bulb and see what happens. And so now, as I plug it into my light bulb, I will have, and this is a little bit ahead, this is the next chapter, I'll have what we call current. I will have the electrons coming off of this plate, going through the light bulb and back to the other plate. And now those charges are going through, they give their energy to that little light bulb there. And so the light bulb operates for a while until it runs out, and it depends how much you put on here. So that's why I picked this big one, because you can you still see it? It's still barely going. Obviously we're getting very low here in terms of how much charge is actually here, because it's barely glowing. So it's not like I'm going to use this light for very long here, and so it doesn't really replace batteries yet, as somebody was asking me about last time. But in the future, hopefully, and we'll have capacitors that can get a lot of charge. And so usually these are used for a lot of other things other than saying, hey, let's run the lights at night and those kind of things. In fact, it kind of reminds me of the years ago when I worked for McDonnell Douglas. We had a room, it was about this big. It was all capacitors. Capacitors, 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 capacitors. And its point was simply this, that there was so much charge on there that it could run our computer system for about 15 seconds. Ooh. But it made a big difference because here's why. You know, we had a computer system running that if the power was interrupted, which in the years I worked there happened one time, actually a car accident out front crashed into the transformer out front and blew out all the power. And what happened then is as the wires went down, as the power grid went down, the capacitors took over. Meanwhile, a room adjacent to this was a giant diesel generator. And so now the diesel engine automatically started up and the generator started up, which took about 5 to 10 seconds to get running full operational, which then would supply the backup power. And it was that point was that intermittent idea here is, hey, this is my backup things. And so we got a little backup. I understand from our medical crew that this is a lot in operational rooms. It makes sense. I mean, can you imagine somebody in an operating room and the power goes out? You know, your brain surgery was going really well. But there was an accident out front. Power went down. Your father's dead. And so, but the surgery was really going well. It wasn't the surgery. So, you know, they have all these backup powers for just those reasons. Question? No?
What determines how fast it discharges?
How fast? Good question. Let me not try to answer that too much because that's coming up in the next chapters. But that's where we're leading. We're trying to apply this. But how fast it discharges, of course, is it's racing through that light bulb. And so what we'll eventually call, if you've ever heard the word resistance, how well can those electrons flow through? And so maybe a good analogy to give you right now is if this you think of as a tank of water, how quickly does this tank drain kind of depends on what size of pipe you're trying to shove that water through.
And the same thing for filling it up.
And the same thing for filling it up. Sure. But notice I did not try to fill it up through here. I filled it up through here. And these wires are much fatter than that little filament. So it takes a long time for all the electrons to go through that little filament. I'll call it 30 seconds. I didn't really count it, but let's say it took 30 seconds. When I hook this up, it probably took less than a second. And in fact, you might even notice it. There's a little red light. And this thing is currently set that if you start asking too much current, the red light will come on. See, there it is. Red light comes on. Now it's probably full. So that probably took about a second to fill that. That was the computer on here taking over. The voltage went down because the computer on here said, hey, you're asking for too much current based on this knob setting. So I'm going to lower the voltage for you because you didn't want more current than this. So that really wasn't part of the physics. That was part of what we call the current limiting. This is a smart little guy. Okay? If I were to discharge it again and turn it up really high, okay, that's telling the computer on board, don't lower the voltage until the current gets to this much higher setting. And it may not ever get there. And then you won't see the voltage go down. So I'm kind of curious myself. Although it's not completely discharged, I'll do that. That should help it a little quicker. And so I'm kind of curious myself if the little red light will go on. Now, so it never went above that limit. Red light never came on, and the computer never dropped the voltage to save it. So that's a little more. That's the other machinery. That's the current limiter. Well, I'll show you one more because, again, it's just fun. But here's another capacitor. Okay, this happens to be the one I was saying. It's 10 microfarads. And so what it means is I would be putting 10 microcoulombs of charge for every 1 volt. Okay, so I have a different power supply. It's this one over here. Maybe I'll even turn it towards you so you can maybe see it here. It's bigger in size, mostly because it's old-fashioned here, and it's made out of a bunch of vacuum tubes. But what's nice about it is this setting here can go up to 400 volts. And, yeah, well, I won't touch it. But that one is at 5 volts, right? Now, if I were then to say, I'm going to hook up that capacitor. I always lose the pins. All right. If I'm going to hook up this capacitor and then crank up the dial to 400 volts, how much charge is going to be on this plate? Yeah, we'll try it. So there is the equation. The capacitance is 10 microfarads. I'm going to charge it up to 400 volts. And my question for you is, how much charge? And so I think you get the idea. You get 10 microcoulombs for every volt. So you'd multiply by 400. So I have 400 times 10 microfarads is giving me the charge. And so obviously a 10 times a 400 is 4,000. 4,000 micro what? Well, what's a farad? Well, I'll leave the micro alone, but the farad is coulomb per volt, right? So the volt cancels off, and I would get 4,000 microcoulombs. Or maybe I should just say 4 millicoulombs. Or 4 times 10 to the minus 3 coulombs. So there's your first calculation. Obviously not a hard one, but hopefully getting the idea that I am not saying that there is only 10 microcoulombs of charge on this. I'm saying there's 10 microcoulombs of charge for every volt. Yeah.
How do you know the maximum charge of the capacitor?
Oh, good question, and maybe I'll kind of address that now. I was going to wait a little bit later, but there is a maximum. Can you kind of see what might happen if I got the voltage too large? What would happen? Yeah, remember that Van de Graaff I had, and I had positive and negative. At some point, I could have so much charge that there's so much electrical forces between the positives and negatives that they will jump across, even though there is the air, even though there is the insulator. And so we like to say there's really never any such thing as a perfect insulator. There is some point where the forces will make it go through the material, or the vacuum of space if there was, no material in there. Okay? So how much voltage really depends on what material you place in there, plus how far apart you put it. Okay? Because you saw when I was doing that Van de Graaff, if I were to hold the other ball way over there, it wouldn't make the spark, even though it's about 100,000 volts. When I got close enough, then it would jump. So there is a limiting value, and that limiting value is not easy to see. We're going to talk about it probably next time, not now, but we will get some numbers in a chart. And if it's made out of air in between there, then there's one limit. If it's made out of a vinyl, as we do, or paper, or all the other materials, you'll see that. But it's based upon that distance. That's why this one is so big compared to this one. Now when I say big, I mean physical in size now, not its capacitance. Because this one can handle up to 600 volts. And so these metal plates are actually physically quite far apart from each other. Okay? And that's why it needs a good physical size. Whereas this one, these metal plates are really close to each other. That's how you get such a large capacitance. But unfortunately, it can't handle a lot of voltage. And the only way to know it is you just read it on the side. It's stamped there. This one says it can handle up to 5.5 volts. So that's why I set it on 5, and I was okay. But I start getting higher than that, I risk damaging it. Probably won't exactly happen at 5.5. In fact, I've actually charged them to 6 before, but just to see if that would happen. And they were okay, but I'm sure 7 will probably fry it, or 8. And this one I'd have to go over 600 to fry. That's why this I'm going to turn on and go to 400.
So the main thing that limits our capactor technology is our best insulator?
Yeah. Or size. I mean, just make it the size of this room, Now, that doesn't help you if you want to put it in a cell phone, right? So, yeah, the material science, we had this discussion in lab yesterday, right? I mean, the material science of trying to actually build these ultra capacitors someday is is really coming down to the materials. What kind of materials can you put in between them for your insulator? How close can you get them together? And then that's kind of limiting how much voltage you have. Well, the reason I wanted to hook this one up is, again, as a demonstration to show you that this is a storage device. If I turn it from standby on up, those of you close enough can probably see the voltmeter right there. Right now there is 100 volts. And I'll keep going. That's 200 volts, 250, 300, 350, and 400 volts. So there's a lot of voltage and quite a bit of charge on there. So that's why I want to be careful with my hands here. But what do you think would happen then if I then just took one wire that is over here where the negatives are and put it over here with the positives? Yeah, it's going to discharge. Now, you watched it a moment ago discharge through the light bulb and you saw the energy. I'll do it real quickly now and you'll see the spark. And so if I disconnect it here and tap it here, tell me if you don't see a spark. All right, and so there is all the energy that is stored in that capacitor with whatever that calculates out to. And that's where we're headed. How do you calculate the energy? So how much charge, how much energy is really the idea we're going to see before today's done. And so that kind of lays out what a capacitor is. And one of the reasons of why we are interested in capacitors. Okay? So let's start with the simplest one. Now that we have an idea of the capacitor, this, which we call the parallel plate one, is the simplest of the capacitors I can make here. So I'll start there and say, all right, let's study this first one. Let's actually just build one with two parallel pieces of metal. Okay, and it looks like that one or that one there. So let me not draw another figure, but say, okay, how do I calculate its capacitance? C. Well, you know it has to do with the charge needed to move per volt. All right, so let's ask that. Let's go back a chapter. How do I get the voltage? All right. Well, I guess I get the voltage from the electric field. Right? How do I get the electric field? How about from Gauss's law? Right? And so what I want to emphasize is I don't think the chapter here is so difficult compared to the other ones at all. In fact, most of the work we're going to do in this chapter really makes us go back to the past chapters. So let me kind of repeat here. I'll start here. Gauss's law. How do I get the electric field between two plates like this? Do you remember how we did it? Yeah, we made a surface. Why don't I go ahead and just make a little Gaussian surface? It was kind of this cylinder looking thing here. And we said, all right, if you are going to get the electric field between these two, that electric field was, and maybe I'll just go right here, the integral of E dot dA over the first surface, over the second surface, and over the third surface is equal to the charge inside over epsilon. And I think you remember the results on this one. At least I'm hoping you remember the results on this one. This is the fundamental one. This is the one that is so important. We use it a lot. It's just a nice way of making a nice uniform field. And so I picked the three surfaces because as I make a cylinder, if I call this 1, 2, and the wraparound part, the face 3, and I look at the electric field from that, I will hopefully see that I've got an E times an A from the first one. That is, I've got an electric field that has the same value everywhere along this surface here, right? It's pointing outward, which is the same direction as the dA, and so A is the area of that little cylinder face I put there. Then if I go to surface number 2, which is over here, we argued that outside the field was 0, so there is no flux from that back face. We are, yeah, in the back face, we or top or bottom or left, right, cap, whatever you want to call this. This part, the wraparound part, the part I've been calling the face, that electric field on the outside is 0. On the inside it's not 0, but it's pointing perpendicular to the area. And so again, going back 2 chapters, we said that you would get a 0 there, this would be charged inside, this would be epsilon naught, and so the electric field turns out to be charge inside over area over epsilon naught. Charge inside divided by the area of that cylinder is what we called the charge density. And so, hopefully not a surprise, you have remembered that the electric field from 2 parallel plates is the surface charge density divided by the permittivity of free space. So there's the electric field from 2 parallel plates.
Why is it that you put all 3 surfaces?
Right, and all 3. You see all 3?
Yeah.
Okay.
But what if the flux on one face is
No. If I had just one sheet of charge, and then I made a surface, then the electric field would be going in both directions. Okay, like that, like that, like that, like that. I think that's what you're saying. But because of the second plate, which is now negative, and it creates an electric field towards that plate. In this region, they are adding together, but in this region, they are canceling off. And that's, I think, what you're asking about. There is no field there. So outside of our plates, no field. Inside, the 2 fields from the 2 plates add together. Okay? And again, that's what's really nice about this geometry. It's why we use it so much. It's fairly simple. And we get the field, yeah. Oh yeah, now of course, here's where we, kind of deviate from, okay, in our little mathematical models, we say they are infinitely big, right? And because that's part of our Gaussian argument here. When we argued that the electric field was the same everywhere across this face, we did that because if this wall was the charged plate and I'm in front of it, when I look and see all this charge and then I move a little bit and I look back, I'm supposed to see the same charge distribution, and that's only justifiable if they're infinite, okay? Okay. So you're not asking about the surface area, the thickness? Thickness of the plate. Oh, well, no, the thickness of the plate doesn't really matter because when I put the charge on here, regardless of how thick it is, where does the charge go? Yeah, out onto the surface here. So if this is this kind of looks like maybe it's a millimeter thick, but if I had made it 5 millimeters thick, I still got the charges right on the surface there. So the rest of it's not needed. Yeah. So no, that's not what I'm assuming. Now you didn't ask, but I thought you had asked the plates. The plates I'm assuming infinite, and in the real world they're not, so I get approximately the same. Which is why I should point out, those of you who are going to do the lab and those of you who did the lab, you will notice that when you actually hooked up your plates in lab and measure it, you got a different number than what we are giving you the formula for, because our plates are really not infinite. And so you got a slightly different number. And that's to be expected. And for a number of you, I pointed that out in lab yesterday and pointed to the reason why. All right, so step 1 is you got to go back and get the electric field. Whether that means you have to go to Gauss's law or you have to go to Coulomb's law, doesn't really matter. We'll go to Gauss's law, and that's the electric field. So now I can kind of come backwards here, okay, and say, all right, now I got the electric field. How do I get now the voltage? Yeah, well, that was that integral of minus E dot dr, right? We got to integrate the electric field from one surface to another, from one plate to the other. And again, we did this a chapter ago. It's probably worth doing it again here and saying, look, as we move from one plate to another, and so let's just do this. I suppose I should ask, which way do you want to move? Do you want to move from the positive plate to the negative, or would you like to move from the negative to the positive? Anybody have a choice? Okay, this way? All right, so I will move from this plate over to this plate. All right, which of course means I'm going against the field. So should my potential increase or decrease? Should increase, right? I'm going against the field, right? And you'll see that in the little formula here. If I call the beginning point 0, and I go to, say, a distance d, and so I'll just label this as distance d between the plates, I can then put in my negative from the definition. I can then put in my equation for the electric field. I can then change this dr to a dx, because dr is how you're moving through the electric field, and I'm going in the x direction. Okay. Then I would put in the direction or the angle between the direction I am moving and the electric field. And you chose to go this way. So what is that angle? 180 degrees. All right, so I'll put in 180 degrees. Now that becomes important because 180 degrees is -1. -1 with that negative then make a positive. So then I got the integral from 0 to d over sigma over epsilon dx. And so then I just get sigma over epsilon times d, right? For the voltage between them. Notice it's a positive number, right? As it hopefully should be. How would have this been different had I gone this way? Yeah, and I would have got a negative sign there, right? So one thing I should probably emphasize here is when you talk about the capacitance, it really is talking about, and I put it earlier on and forgot to mention it here, but it's really talking about the absolute difference. I mean, obviously, one direction is an increase in voltage, and the other one is a decrease. Fair enough? And I say obviously, I don't know if you're there yet, but obviously, I got to go with the field and against the field, right? There's going to be an electric field set up. And so if I think about going from here to here, there's an increase in voltage. If I go from here back to here, there's a decrease in voltage. But I just want to know the capacitance, so I'm not even going to pay attention to whether the voltage is a positive number or a negative. Just what's the absolute value? It's 400 volts. I didn't bother to tell you that this one was 400 volts more than that one, because I could have hooked it up the other way and it's still 400 volts difference. Yeah.
So when we measure D, are we measuring the back of the plate?
Nope, surface to surface.
So how could the thickness not change? Because the electrons would be pushed to the back side of the plate, right?
Again, maybe I'm not understanding your question. If this is the thickness of the plate here, and this is the thickness of the plate there, the electrons are sitting here. The lack of electrons are there. The electric field does not exist in the metal itself. So the electric field is here. And so I did an integral from the very top surface to there, because that's where the electric field is. So this is d, the distance between them. And if I shave these down, did anything change? No, 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 no. If this plate wasn't here, the answer is yes. If I had just one plate, then the charge would spread out uniform. And if it's infinite, I don't have these edges, but if it's finite, I guess I'd have a few on the edges. But that's what it would look like, and that's why I would get a field in both directions if I had just one plate by itself. But now, when I come along and put a second plate here, which is lacking charges, which by itself would have looked like that. These electrons now have a reason to go over here. The whole reason they spread out before is because they're all negative. They don't want to be over here. But now they've got some positives to be attracted to. And so this guy's going to migrate over to here like that. And now that negative is going to kind of move over to there, making that a positive. This one will then migrate on and through, go to there, chase an electron away, away from here, making that positive. And eventually, this is going to continue until, because they're balanced in charge, everywhere I start an electric field, I terminate an electric field. And that's why I end up with no electric field on the outside. That help? All right. So in the parallel plates, there is no charge on that side anymore because the second one pulled it in. A single plate by itself, I think, is the mental picture you still had. And that, yeah, that would put charges on that side. And if there were charges on that side, then there'd be an electric field on that side. And that's what the presence of the second one did to it. It changed all that. Okay, so now heading back here, I now have a formula that is a positive number. But what I was getting at is even if it wasn't a positive number, I'm going to put it into the formula as a positive number. Okay, so it doesn't matter which way you go. But now let me put this in here. In fact, I'll just jump over here to this side of the board, and I get my first equation for this chapter. What is the equation for the capacitance of two parallel plates? And I should probably emphasize, this is a air field parallel plate, right? There is no materials in between. Like I said, that's going to change. Not today, but next lecture we'll talk about putting materials at the very end of the chapter here. But right now I just have an air field, which is why, of course, as we use this word more and more, this is the permittivity of free space. And maybe I should address that. Free space, they mean vacuum. I don't really have a vacuum here either, right? Pretty close. So unless we're really after something really, really, really accurate, it's the same in a vacuum as it is in air. It changes by very, very, very little. Okay, the multiplication factor of like 1/10,000. Okay, so there's very little change. All right, so like I said, most of this we'll talk about air till the very end of the chapter. But it lets me finish my calculation. Here's the capacitance, charge per volt. And now I have an equation for the voltage. I lost it now. What was it? Sigma epsilon D. And now, let me look at this sigma again. What's sigma? Yeah, it's charge per area. And so now, if I kind of simplify this equation, it's a compound fraction, you'll notice that there's a charge on top and bottom. And you get the equation that 2/3 of you, I just kind of threw at you yesterday, or I threw, and I'm not sure how Don exactly did it, threw it at you there and said, look, this is the equation to calculate the capacitance for an air-filled capacitor. And so you already did, or will be asked today, to measure the size of this plate, get the area of this plate. Measure the distance between them. Knowing the permittivity of free space, get out your calculator and calculate the capacitance. Okay? And it's not much. It's way down in the picofarads. I think we came up with numbers like 140 picofarads, real small capacitance, but very close to what we measured. And then we just took the meter and we measured it. And that was the point of one of, I think it was step 6 in the lab, was to calculate it and then measure it. Okay? And obviously my point here today is to show you about capacitors. What are they? And then how would you calculate the capacitance based on that geometry? Shall we try a different one? Yeah.
For your integration from 0 to E,
I did. Oh, yeah. So somewhere in here I asked you guys, which way do you want me to integrate? In other words, which way do you want me to move along the electric field? This integral here is saying move, dr, along the electric field, and your voltage will increase or decrease depending on which way you go. And when you go against the field, you get to higher potentials. And when you go with the field, you get lower potentials, which hopefully is evident in the fact that you have a negative out in front and a dot product there. Okay. And so, yeah, I needed to pick a direction, and I did. I said, let's call this where I'm starting at 0, and let's move out to there to get a distance d. And again, last week's lab, maybe you remember this quite well, but last week's lab, you took that power supply and you hooked it up here and here, so there were 10 volts in between, and then you took your little probe and you actually then got the voltage at places in between, right? Right in the middle you got 5 volts, and as you got closer to this plate, you got closer to 10 volts, and as you got closer to that plate, you got 0 volts. So you saw how the voltage changed as D moved further and further, and eventually got all the way to 10 when you got to that far plate. Right? And so again, that was the point of last week's lab, to get you a feel for these parallel plates also. Well, as I started to say here, I thought I would do 3 examples of just different geometries, but it's the same logic. Okay? And then we'll move on to something else here. But the idea is, let's try this one. I told you last time, these coaxial cables are used a lot. They've got a lot of nice properties about them, and we'll see that. They also got some disadvantages. We'll see that now, actually, here. But this is a coaxial cable. I'll pass it around again in case anybody didn't get a chance to see it. But again, it's got one wire in the center, okay, then an insulating material, and then a shielding wire on the outside. And then some more insulating on the top so you can't, touch the metal wires there. But if I look at this coaxial cable, and say, draw a picture again, I guess it would look something like this. This is my, darker one here. This is my shielding wire. Okay. And right in the center, I have my signal wire. Okay. All right. So there's my coaxial cable. Now, as I send signals down here, or as I play with this wire, I am going to then charge this up. Maybe this center wire I will make positive. In the process of making it positive, it's because I took electrons off, and I will then send them to the other side. So my power supply, the one that's maybe sending the data from my cable company's headquarters through this cable, through those wires, across the telephone wires there, into my attic, down to my computer, this is that wire. This is that coaxial cable. And so this is going to then be charging and discharging it. Those are my pulses of information. It's going to go on, off, on, off, on, off, on, off, right? It's going to charge it up. So let's just say it goes to charge it up. That means I'm going to get negatives on that inside edge. If I take a cross-sectional view of this, it'll look something like this. Here's the inner wire. Here's the outer wire. This inner wire, I will say, has a radius of r. Oh, and I should use the same one I did last time. Did I call that A or B? A? So r sub A there for the radius of that inside wire. And then I have a radius of the outside wire. Now your questions come up here. Radius to what? Because that outside wire, that shielding wire, has an inner radius and an outer radius. Fair enough? But if you look at this, and again, had nothing to do with this chapter, but last chapter, what does the electric field look like from this structure? Well, this is going to get positive charges. The negatives are then going to be drawn into that inner edge. And so the electric field looks something like this. But is there an electric field actually in this outer shield? No. So when I go to integrate, I'm only going to integrate my electric field from the radius of the inner wire to the inner radius of the outer wire. And that sounds kind of funny, but does that make sense to you? The inner radius of the outer wire. Okay? So what state is north of South Dakota? It's not supposed to be a hard question, but a lot of people will tell you Canada, all right? But it's not, all right? The state that is north of South Dakota is North Dakota, right? All right, so, I got to tell you this. Do you guys, I don't even think it's on the air anymore. It's probably a good thing. But you know all these reality shows that have shown up? I think like Survivor's like been the first and the most popular one. But did you guys ever see one, the Beauty and the Geek? Yeah, a number of years back, and I don't know why I wasted my time watching it, but there was just something about it, you know. And so if you're not familiar with the show, it's the geeky guy. Part of the contest, anyways, is where the geeky guy tries to teach some academic facts, if you will, to the beautiful girl, and then she's got to go in on her own and take this test, if you will, you know. And if they fail, they get kicked off the show, and they don't win the $50,000 or whatever it is at the end, right? So the question literally was, what state is west of Virginia? West of Virginia. It's like, come on. West Virginia? I mean, could it get any easier? No, she missed it. They got kicked off. I think our answer was Boston. Boston. It's almost as bad, or maybe that's worse than when I was at Disneyland. They had one of these shows and there was a contest, and the comedian was up there and they were playing around, and they grabbed the guy from the show and he said, hey. The guy was claiming to have all knowledge, and he goes, all right, I'll test you. And he goes, I know the capital of any country in the world. He goes, all right. The guy stands up and says, what's the capital of Africa? What? Is Africa a country? Of course, there is an answer to that, you know. What is the capital of Africa? A. Yeah, so test me, right? I know the capital of every state. Anybody want to test me? Yeah, I know you're thinking. Iowa. Is it Des Moines?
No, I'm pretty sure it's that.
No, I was being more serious with the Des Moines, but anyway, I don't know what the capital is. All right. How'd I get on that? All right, so back to this here. All right, so here is this electric field. And so here's my question for you. My question is, what would be the capacitance of this wire? If this wire is going to string, and in my case, it happens to be 19,775 feet from my house over to the cable company. I'll tell you later why I know that, but anyways, that is the distance from my house over to the cable company. And so what is the capacitance of that wire, you know? And of course, why is it relevant? You'll see here in a second here. But I'll just start with that question. What would be the formula for calculating the capacitance for that geometric shape? I'll start with, do you think it'll come out to be the same equation? No. Why not? Well, because the capacitance depends on the voltage. The voltage depends on the electric field. The electric field depends upon the geometry of those shapes and that distribution. So it's not going to be the same formula. I need to work it out here. So I will start here. I will do that same kind of pattern. I will say, all right, let's find the capacitance, charge per volt. Right? Now, in order to do that, I need to know the voltage between the inner radius and the inner radius of the outer conductor. Oh, that's how we got on that. Yeah. The inner radius of the outer conductor. Okay? And so to get that voltage, I will integrate the electric field from one conductor to the other. But in order to do that, I've got to know the electric field. Right? And so going through the same thing, taking back a couple chapters, there's my beginning point. What is the electric field for this geometry? So we've done it before. It's a good review to do it again. Given that the test is coming up fairly soon, let's do a Gaussian surface. So maybe in green here, I will draw a little Gaussian surface that is mathematically centered with a radius of r, some distance, you know, in between my two conductors. Okay? And so if I then go ahead and apply Gauss's law again, E dot dA is equal to the charge inside over epsilon naught, I will get the electric field. And hopefully it'll be the same one we got before. By the way, did you notice something important here? I have not memorized the electric field between these two. I'm going to work it out. Now, you have a choice. Do you want to memorize it? It's different between that and the parallel plate, right? And if you start memorizing all of these, you're going to think, wow, there's a lot of formulas here to memorize. All right? And then you're missing that deeper road that I keep saying. And now there it is, top of the syllabus again. I can't resist it. Right? What does it say? Physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. Okay? So I don't need to memorize all these formulas again and again and again. Hopefully you won't need to be there also. I know that is a big step, and so maybe your backup is, hey, I'm just going to memorize all these formulas here. But see if it doesn't work out to the same thing you got. Just do it again and again and again. And that's what I'm going to do. I'm just going to apply Gauss's law again. I find capacitance, I got to get voltage. Okay, to get voltage, I got to get the electric field. All right, so what was or what is that formula? I don't know. I forgot it, but I can work it out real quick here. So I'm going to do a Gauss's law. So here's my surface. If you remember us doing this Gaussian surface, we did say the Gaussian surface had a length L. It has a radius of r here, and we are going to then do the integral. Now again, the integral would have technically 3 pieces, because we have to do it over a closed surface. But as we look at this, what I would call, say, the left cap and the right cap and left cap here, as I cap those, I would look at this electric field, and as we argued in past chapters, is the symmetry of this charge dictates to me that the electric field has to be radially outward. Right? And because it's radially outward, the flux I get from the left and right caps are each 0. And so if these first 2 integrals represent the caps, I get 0. The one that doesn't come out to be 0 is the wraparound one, what I keep calling the face. And so as I look at that one, the electric field goes straight outward. So the angle between the electric field and the area vector is 0, as well as the argument from symmetry that the electric field has the same value everywhere along that Gaussian surface, leads to E times the area. Now, the area then is where I go back to my geometry. How do you get the area of this wraparound piece? Well, its length is L, and its distance would be a circumference, a 2 pi r. So I will write it as L times 2 pi r. Now the charge inside is going to depend also on what your L is, because this would be charged up with some linear charge density, which we kept calling lambda. So the charge inside would be lambda over L. And as I've mentioned many times, fortunately, the L cancels off, because again, I don't want that. Not that I don't want it, but just I should not show up in my answer, because that is just a mathematical surface that I'm creating to do an integral, but the field should be independent of that. The field should be dependent upon charges and distances. So sure enough, I end up with 1 over 2 pi epsilon naught lambda over r. So there is the electric field from this shape. And again, notice that part has nothing to do with this new part of the chapter. But it is a good time to review and let these things start sinking in. And you know, that's why I said I think this makes a good test time, that we're not really getting too much new information here in this new chapter. We're applying what we already know to certain scenarios. Now, once I know that electric field, I can now get the voltage between those two surfaces. And that integral we've already done. I'm going to do it again, partly as a review, partly to emphasize that, you know, I don't memorize the equation of the voltage between these two. Makes no sense to me. Then I'm just going to have a long list of equations that inevitably I'm going to mix up, and I'm going to forget. It's the fundamental principles that get me started here. So then I'm going to get the electric field between those two faces. So the electric field was defined last chapter as from some initial point to some final point as E dot dr. It is how that electric field changes as you move along from one surface to another. So I would have to ask again, I'm going to go from one surface to another. Do you want to start at the inner radius and go out, or outer radius and go in? Anybody care? The only thing it's going to make is a 0 degrees or 180 degrees, right? But likewise, I said, I'm not even going to care about the plus or minus anyways, just what is the voltage. So I kind of heard it both ways. I think I heard more people saying go from the out in. That's often how we do R, so I will do that. Plus the way I set it up, that means I go in the direction of the electric field. And maybe that's good, because that's the opposite of what I did last time. So when I go with the electric field, will the voltage increase or decrease? Yeah, it should decrease. Let's see what this comes out to be. It would look like this. I'd have a minus. I guess I would start at the inner radius, RA, and go to the inner radius of the outer conductor. And so there's my RB. My electric field would be 1 over 2 pi epsilon lambda over r. And then I would be integrating in a dr direction as I'm moving out. And if you want to have completeness here, I guess I would have cosine of 0, which is just 1. But that is the direction I am moving out. So I'm moving out, moving out, moving out. There's dr. That's the direction of the electric field. Okay. So, not too surprising, I do get a negative number there. As I pull out my constants, is my lambda, my 2 pi, my epsilon. Those all go out. And then I have an integral of 1 over r. And we saw this one last chapter here. What's the integral of 1 over r? Yeah, that's the natural log, right? So it's the natural log of r evaluated from RA to RB. And so this becomes negative lambda over 2 pi epsilon. And then this would be ln of RB over RA. Okay. And so there's my voltage change. And not worrying about pluses or minus, I would put, okay, my voltage change is just a lambda over 2 pi epsilon natural log of RB over RA. And now finally I can get to the step that has anything to do with this chapter, but I don't want to belittle that because I think these are the hard steps of it, the old stuff. That's why I said this makes a good time to kind of review and go through this. But what's new for this chapter here is what's the capacitance then of this geometric shape. So I can finish the problem now by saying the capacitance is the charge that's on there divided by its voltage. And its voltage is lambda over 2 pi epsilon ln of RB over RA. And you might at this point then want to go, well, wait a minute. How much charge do you have on this wire? Can you kind of see now where the amount of charge would depend on how long this wire is, right? As I said, if this wire is 19,775 feet, you have a place to put a lot of charge on there, whereas somebody living closer to the cable company only maybe has 1,000 feet of wire, and so therefore they're going to have less charge in it. Now that doesn't mean they have less capacitance, and let me illustrate here. But watch this. As I make this final step here, the charge that is on there comes from here. What is lambda? Charge per length. So it's the total charge on that wire divided by its length. And so hopefully not too surprising after the last calculation we did, but we'll see that the charges cancel off. And the capacitance then depends on the geometric factors, right? Now we had here, the capacitance depends on how much area you are putting the charges, and then D, how far apart do you have to separate those charges? Because capacitance is this, charge per voltage, okay? And you see the same thing here. You see that the amount of charge on it doesn't matter. So the capacitance is a given number. It doesn't matter if it is charged or uncharged. It doesn't matter if you have a lot of charge or a little charge. The capacitance is the same number. The capacitance depends on its geometry. What shape do you have? How much surface area do you have? How far apart are the conductors? And that's what this is saying here, right? My capacitance depends on the R's, the inner radius and the outer radius, right? This, and then how long is it? So something that's really long would be like this plate having a lot of surface. And so I would expect to get more capacitance, right? And so it depends on how long it is. That's why I happen to know that it's 19,775 feet, because the speed of my cable sucks. Why does it suck? Well, how do these things work? Well, back here, there is a little charger, right, that's sending signals down this cable. So it's got to charge this up to 5 volts. So we're going to charge it up to 5 volts. How much charge do you need to get to 5 volts depends on how much capacitance. So if you have a lot of capacitance, which means you have a long length, it's going to take a long time to build up that charge. So the first piece of data takes a long time. Then it's got a discharge. Then the next one. And so my data is coming in like this. And my friend who lives 1,000 feet away is like that. Right? And so the rate at which it is does matter. And so in this case, I would say that the capacitance is really not an enjoyable property of our electronics. One that I can't avoid, and it does affect the speed of my connection, and for that matter, the speed of your connection here. Is how long is that cable? What capacitance does it have? And other properties too we'll soon learn. What inductance does it have here? But that's why when I saw the little cable guy going down the street, I said, is there anything we can do about the speed of this thing? Oh, 19,700. No, that's the best you're going to get. Sorry, sir. Yeah. So unless I live closer, or they change the length, or I go with another company, that's what I have. Oh, it's not a linear function, so it would actually help. Yes. Yeah. It would help. Yeah. Why it's not linear is not so obvious. There's also what we call dispersion effects here, and that's where it would make a difference. Yeah. So one in the middle. Yeah. So it does help, and then they start adding more nodes on there. So you know, as networks get better and better and faster, it's because they've done different cabling systems. The old ones would just take a twisted pair of wires, and then you could, you know, your data is very limited. You know, what's the DSL thing, or the old dial-up? You guys are too young to remember old dial-up. There was 54K or something like that. Then the twisted lead, and yeah. So they changed the geometry of the cable, but that's expensive to put in a whole new cable. And then you do change the nodes and how far you have to send it before the next one. And even better still is if they do that, oftentimes they'll do something like this, and this is what they eventually will do, so I'm told. But if, you know, here's the main office, and here's a little box hanging on the telephone pole, maybe a couple of blocks from my house, and then this one goes to my house. You invest more money and resources in this cable. And in today's world, that means you're hooking fiber optics between here. And so it will go lightning quick to here, and now it's just got to go a short distance on the old cable. So your backbone will be all this fiber optics. So, and we live in an interesting area because we have all that traffic. You may not realize, but all those fiber cables that are laid to Asia come right into our coast here at Morro Bay. And so that's where they all come in. And then they split north and south, and everything going to LA, everything going to the southern part of the United States comes right down our train tracks. Fiber optics buried under there. Yeah. You want to really mess up LA, just dig a big hole under the train tracks. You will destroy that. And there's little signs as you drive by. You see it really knows out at the Gaviota coast there. You know, if you park and you cross the tracks, you know, big signs. Underground phone line. Do not dig here, you know. Call before you dig, you know. And so it's, yeah, big one. All right, well, let's try one more. I said we would do 3 here. And so I've done 2. I've done the parallel plate and I've done the coaxial cable. One more and we'll shift gears to some other nice ideas of these capacitors. Because this is the general fundamental physics. This isn't really kind of using them quite yet. And that's what we want to get to. But let's see if I put it in my notes. Yeah, now that we've got the coaxial cable, let's do the concentric shells. And so I will ask then, what is the capacitance of two concentric, and just emphasize conducting shells. So I'll take the first one and the second one. This will be kind of my cross-sectional view. Maybe I'll use the same notation, that this will be a radius of RA. So there's my radius of my inner conductor. Maybe I'll give some thickness to the outer conductor. I'm only going to be interested in the part that is between them anyway. So again, RB, the inner radius of the outer conductor here. And then say, all right, what is the capacitance of this geometry? And again, hopefully by the time we've done these three, you see that the capacitance is going to depend on the geometry, because the electric field and the voltage depends upon the geometry here. It won't depend on how much charge I place there. All right, so let's take, like I said, this shape here. Now this one, I think, A, it's our third one. B, I think because it's spheres, they're a little easier to work with. I think you already know this. I probably don't even have to work it out from the beginning, but maybe I better at least ask. Do we know the electric field? If I were to, say, charge this up to a positive Q. Good question. Hang on, I'll put the outside negative. And so I've got a negative Q on here. Yeah, obviously I could do it either way, right? I could chart, so there's, hopefully you see it's going to be the same with whichever way I do it. But yes, it is conventional, as you said, to what we call ground the outer conductor. And so the outer conductor is the one that is at the same voltage as the earth. So you take a wire and you connect it. And so if this outer layer of insulation is removed, you know, so I go here and I remove this outer layer, the first wire I come to is not dangerous. Ouch, other than it poke me. Maybe it is dangerous. But this outer one here is, you know, you can touch it, put your tongue on it, you know. It's the inner one that's going to have the high voltage and the one that can shock you. Okay. And you see the same thing with your plugs. Don't try this, but you know, one is connected to the earth, and they usually label it, but if you look at a plug, it's a little fatter. You know, that's the one if somebody accidentally sticks their finger in, you hope, oh, was it the big one? Please? You know, and so nobody gets hurt by touching that one. It's the other one that has a lot of voltage and a lot of power and can do a lot of harm. Okay. Anyway, so I'll go back to this. I'll even draw the electric field in here again. So the electric field would look something like this. But I'll just ask you, do you know the equation for the electric field? Or do we need to do Gauss's law here? Gauss's law? All right. But I hope I get the same thing for a point charge. Right? And so if I apply Gauss's law, I would go the integral of E dot dA is equal to the charge inside over epsilon naught. And so I'm just going to take a Gaussian surface, a Gaussian sphere all the way around it. So there's only one surface to do. My argument is going to be, just like we did many chapters ago with symmetry, that if I were to walk anywhere on this Gaussian surface, as I look around me, the charge distribution is exactly the same. Hence, the electric field is a constant over that surface, so I pull it out. Also, as I look at that distribution, I can argue that the electric field is radially outward. And radially outward means that the direction of the field and the direction of the surface from the Gaussian surface are in the same direction. So this reduces down to something that looks like this, which then reduces down to something that looks like this, which then reduces down to something that looks like that, right? Where we have electric field times area. The area of a sphere is 4 pi r squared, okay? So there is the one side of the equation for Gauss's law. The other side would be, I'll call it Q over epsilon, and I'll just carry it all the way down to there, Q over epsilon. That is the charge inside, and so that's what I've said in here. How much charge do I have on that little ball in there. So when I simplify this, I get the electric field from a ball, which is the same as the electric field from a point charge, right? All right, so there is the electric field between those two. And so that's why I was asking, haven't we seen this before? All right, so it's going to come out to the same thing that we did before. And in fact, we also found the voltage difference between a point charge, and we maybe should integrate that one too. And so if I look at the voltage, I would go minus E dot dr. But again, we did this one. And I'm hoping you remember the equation for the potential from a point charge. That was so important in the last chapter. That's how we got things that weren't points, by adding up a bunch of points, right? Wasn't it 1 over 4 pi epsilon naught q over r without a square in it? So we should get the same thing here. Now we need to integrate from some initial to some final. I should ask it again, which way do you want me to go? Okay, same idea. Inner radius to the inner radius of the outer conductor. All right, so in this diagram, this would be an integral from RA to RB. There's the negative. The electric field is what I just calculated from Gauss's law. I will then move along. As I move from this inner conductor to this outer conductor, I would be moving in the direction of the electric field. Well, this is r squared because it's electric field. And now once I do an integral, I will get to the familiar just 1 over r down in the bottom. Okay. And that's why I was kind of asking, should I even do these integrals? And it sounded like you guys wanted me to, so I'll do them again. All right, but obviously they're going to come out to be the same as we did before. And they're the little point charges, so those are the ones that really you should have in your memory. Whereas all these other electric fields, you probably should just work them out. But those little, that Coulomb's law, you wanted to add up the electric field from a bunch of point charges, or you wanted to know the voltage from a bunch of point charges. Okay? And we can then do this integral. Now I'll put the negative out here. I'll put my constants, 1 over 4 pi epsilon naught. I'll bring the q out. But this integral then would be a minus 1 over r, evaluated from RA to RB. I guess that will allow my negatives to cancel off. And I will get a q over a 4 pi epsilon naught, and then 1 over RB minus 1 over RA. And so the first term would be the voltage on surface B, and the second term would be the voltage on surface A. So the voltage difference from A to B would be something like this. Now you may argue that that's a negative number. Now it should be, right? Didn't I go with the field? So I should come out to be a negative number. And it would be, because RA is smaller than RB. So when you do the reciprocals, this negative number is bigger than that positive number. So this is really a negative number. So I guess if I really just want to make one more intermediate step and say, okay, what's the absolute value? Then maybe I will change the order and write it as 1 over RA minus 1 over RB. But then on the other hand, if you realize capacitance, we're talking about absolute values anyways. If I put that into my little calculator and came up with a negative number, that of course I would ignore the negative. Although that's probably not a good general rule, because if you come up with a negative, that should be a clue that you did something wrong. But at least go back and see what it was. And in this case, I didn't take the absolute value of the voltage. So that's why that one came out to be negative. I went with it. But this would be the voltage. So finally now I can get to this chapter, right? What is the capacitance for these concentric shells? And so it would be the charge you placed on there divided by this voltage, Q over 4 pi epsilon naught 1 over RA minus 1 over RB. And again, it's a compound fraction. Q's canceling off. So I'll get a 4 pi epsilon naught. And then I will get a 1 over RA minus 1 over RB. Which, oddly enough, I like it written that way, but you might argue that's a compound fraction too. So if you want to simplify it one more step, I don't really like it. It kind of merges the two R's together and kind of takes away from my physical understanding of it and just gives me a formula. And I'm never really crazy about just plug and chug into it, but that would look a little more simpler mathematically. But again, notice that it depends on geometry, right? It depends on radius, RA, and RB. So the capacitance depends on geometry. Oh, would I want you, like on a test? Oh, I would take it either way. No, this is great. This is great. This is even fine. You know, yeah. It kind of, yeah. Well, as I said, I wanted to show you 3 good examples of calculating capacitance before we kind of make this next step, huh? Yeah. The coaxial cable one? This one here? Yeah.
We did 2 kind of capacitance calculations. What was the difference? Because you got one for a cylinder, one for a sphere.
Yeah. So I've done 3. The first one we got was the parallel plate. And we got that. So if you have 2 metal plates parallel, this would be the formula for the capacitor. The next one we got, I'll look it up here.
There was 2 pi R.
2 pi. No, didn't it have like a epsilon L natural log? Are these the 2 you're asking about? So this is a formula for a coaxial cable. So I would choose which one depending on the problem, right? If the problem is giving me something that looks like this, then it looks like parallel plates to me. And I'd use that top formula. If they gave me something that looked like this, then I'd use that next one. If they gave me something, and I don't really have a good demonstration, but a sphere, with a sphere wrapped around it, then I would use this one. Is that what you meant by I gave you different formulas? Yeah. So again, yes, I did give you different formulas for different geometries. And so we've got to look at the geometry. Okay. And that's the point. The point is, what is capacitance and how would you calculate it, and how, of course, would it be different based on different geometries? And so we got to go back and do electric fields and potentials and get the capacitance. Okay. All right, well, as I said, and maybe spent a little too much time there on those calculations, but like I said, I think doing the calculations ends up being a nice review of Gauss's law and potentials to find these. But let me kind of shift gears a little bit with you and talk a little bit more about just using this capacitor. Okay? I'll start with a little symbol here. If I come along and I put this on the board, Or maybe even if I lay it out this way on the board. This is how I'm going to indicate to you I'm talking about a capacitor. Okay, fair enough? So a little symbolism here. Now, it may look like this one. Or it may not even look like that. Isn't this a capacitor too? But it doesn't really look like that. Fair enough? We're still going to use that symbol. Okay? So when we put I put a little symbol on the board here. I'm not going to worry about its geometry. Now I need its geometry to calculate its capacitance. Or I could just be told its capacitance. And then I don't care what its geometry is. If I look at this little guy, I don't need to know that it's probably a rectangular set of metal plates that are rolled up. I just know its capacitance. It could be a series of coaxial metal ones. It might be. I don't think it is. I haven't taken it apart, so I really don't know. It doesn't matter. What I do know is the outside says it has a capacitance of 1 microfarad. Fair enough? All right. So you're going to see this symbol, and depending on how I want to draw it, you know, I may lay it this way, I may lay it that way, but you lay it anywhere like that, it is a capacitor. Like I said, whether it really is 2 parallel plates, long rectangle rolled together, cylinder shells like a bunch of cans of soda stacked inside of each other, I don't know. Doesn't matter. They could even be spherical ones, although the spherical ones aren't really that common. It doesn't matter. These little guys, these are actually parallel plates too. They're just 2 tiny plates right next to each other, and then some insulating material put over. But once I know its capacitance, you know, and then it just says right on them, then I got it. Okay? And so sometimes we will care about its geometry, because its geometry does affect its capacitance. But other times we'll just be told its capacitance, and then we'll just use it. So that's what I'm going to do from here forward in the chapter. I'm just going to draw a little symbol like that. That is the symbol for a capacitor. Yeah?
How would you use the spherical?
I don't have a good example for you. I used it to show you the academic side of, see how it's going to change with geometry? See how you could calculate it. But I don't have a good answer for you of where it would show it. Yeah. All right. Now, yeah, I should try to find one. I would be interested. Wouldn't surprise me if it, you know, in some kind of little tiny experiments, either experiments of science or the engineering of microprocessors, that you got little chunks of charges that are not very long, not very tall, and, you know, kind of symbolizing a transistor, and so maybe you're charging that thinner one up and down, and so maybe you model it as concentric spheres. So it wouldn't surprise me if there's something closely related, but I don't know of anything. Yeah. Okay, well, so there's step 1. So let's try it again here. Let's come back to what I showed you earlier. Oops, I guess I left this one on. Doesn't really matter, I guess. But here is the capacitor. So when I say, they look the same? And as I joked with the guys in lab, and for the rest of you today, is I will hold these up. And one of the tough skills to learn here is drawing it in your book or on a piece of paper, and then holding it in your hand and saying, does this look like that? And so translating a picture into the real world at times can get a little challenging here. And that's why we did with the lab. And that's why I joked with you guys on yesterday about it. And I will for the others of you today. I'll hold it up there and say, okay, this picture on the board, does it look like this? And the first time you do it, you probably say, no. But fortunately, if we start with some simple ones, and then they get harder and harder and harder. Okay? And some of these will get really complex. So there's the first one. So again, if I were to draw this on the board, what I mean is grab this and put it on the table. Okay? So there is my capacitor. And I'll move the other ones away. If I wanted 2, I would draw 2 symbols on the board. 5 symbols. Okay? But for starters, I just want 1. And so here's what I'm going to do. I'm going to say, okay, let's take that capacitor. Let me just kind of move that one right here. Okay, so here's my capacitor. and let me hook it to a power supply. Right? That's what I was doing earlier. All right. So, power supply. Well, what does that look like? You'll never guess this one. There we go. All right, so new symbol for you, our second new symbol. When you see something like this, these two plates, and if you're kind of into the understanding of it, it actually comes not so much from this. This is a little more modern technology than just a car battery. You know what a car battery looks like? Like that, right? It's plates of lead dipped in sulfuric acid. Right? And so they have that symbol. So if you have just one set of plates, you draw it like that. If you have like a car battery, has 6 of them, you would draw a series of 6 of them. It would look something like this. But truth be told, we get kind of lazy and say, you know what? Let's not draw all of them. That's just my power supply. And truth be told, today we don't even use the batteries. We use the wall socket, a lot of fancy electronics in here, and we generate our own. So I'll set this and turn it on to 6 volts. Oh, 5 volts. That's only 5.5, right? All right, 5 volts. 5 volts. Okay? So, maybe I should ask again. Does that look like that? Does that look like that? Okay, so like I said, it takes a little while to make that connection. Now, next step here. Let me actually hook it up. Let me then take the positive side and hook it here, and the negative side and hook it there. Okay? So I'm going to hook it up. I'm going to hook it up with what? That's what these wires are. Yeah. Does that look like that? That one's pretty good, I think, right? Right. That one there? All right, so some of you, this is your first time. Others of you, you've done this for a while. Okay? But this is the symbolism we use for our circuitry. Okay? This picture here, if I saw this picture in my homework, it would mean something to me. If I saw this picture in the lab, I could actually hook it up, right? This is what it would tell me. It would say, get the power supply, set it to 5 volts. So I did that. Get a capacitor. Got it. Hook the positive side to one of the plates on the capacitor. Right? So positive side. Traditionally we use red, so maybe I'll switch over to red. So red, I'll do right there. The other side, the negative side. Black. Hook it to there. Ta-da! And that's what you saw me do earlier. I didn't draw the picture for you, and now we want to go a step further, but that is what that symbol means. It says, take 5 volts, hook it to your capacitor. Okay? Now, let's talk about more detail of this. What is happening the moment I hook it all up? As soon as I hook all the last wire gets hooked up, what begins to happen? Why do we call this the negative side of the power supply? Yeah, it has a lower potential than the higher side, right? Now, if it has a lower potential, that means this is where the electrons are, right? And this is where the electrons are lacking, right? That's why it's positive. So what would happen to these electrons that are in this power supply? Now that I've hooked it with a conductor, what's it going to do? Yeah, they're going to move, right? They're going to go out, they're going to go through this wire, they're going to move along, and they're going to go onto this surface. And so what might happen at first is I would put 1 electron on there. Now, that's not all that happens. What happens next? That 1 electron will then chase an electron on the other side of that capacitor. Right? Now, please hear this carefully. Did I say the electron went from here to here? No. The electron did go from here through the wire and onto that plate. Now it stopped. Has nowhere to go, right? The air is an insulator. But that doesn't mean it can't push through the electric field. So in other words, there is, as we've been talking about, an electric field that is established between those two parallel plates. So that one negative charge on that plate then pushes another negative charge. And what happens then is it continues on around and finishes the rest of the circuitry in here. Without getting too much into the electronics, or maybe going old school where this is coming from a chemical reaction, what will happen is the first chemical reaction has to complete itself before the next one. So we got to send one electron, the next one's got to come in, that finishes the redox reaction, and then the next one starts. So the next one starts. It sends another electron out. Oh, now wait a minute, where does it go? I guess it will go on that plate too, but does it really want to go there? Well, isn't it being repelled from that one? Okay, so it will still go there because there are so many negatives in here that it would rather go over here where it is less crowded, which, by the way, anybody on Thursday's lab who wants to show up Wednesday morning, you're welcome again, right? All right, so I just want to keep selling that. I know we're packed in there on Thursday afternoon here, and it's really empty. Oh, and Wednesday at 11, if you can fit that in your schedule. I was surprised how many people actually then kind of migrated at Wednesday at 11. So if you're on Thursday and you want a little more space, and you know, if you can, obviously, if it fits into your schedule, head on over to the other labs, trying to get them more balanced. And that's what this is. It's trying to get more balanced. It's leaving these and going on to there. And the same thing would happen. What would happen is it would create then an electric field. That electric field would then push on another electron, and it would complete the circuit. And then it would do it again and again. Would it keep doing this forever, though? What's eventually going to happen? Okay, let's say the battery doesn't die. All right? Let's say I got this thing plugged in and I got reliable energy. But still, is this going to keep going forever? No. It is not. Why not? Okay, at some point, can you begin to see that there gets to be enough concentration of charge? Or put another way, there gets to be such a strong electric field here that this electron that is being forced out by the battery or the electronics in here is not strong enough to overcome that. Fair enough? When will that happen? Yeah, when they get to the same voltage, right? If it helps, think about this as water. This is a big tank. If I had a big tank of water right here and it was filled up to the top of my head and I came along and I had another tank, and maybe not nearly as big as this tank, so I won't worry about the water level going down on this big tank. So I got this big tank over here, but over here I got this small column. And I took a rubber hose and I connected it and I opened the valve. Would the water flow out of the bottom of this big tank and over to here? And wouldn't it start filling up this column? And the water would come in and come in and come in, and when would it stop? Right, and from back to our physics 121, it would go when the pressures, the forces are balanced, right? Does that mean you have the same amount of water in this little tank as this big one? No, what do you have the same? The pressure there, right? Pushing them back. And that's what I'm trying to say here. I am in no way trying to say that the amount of charge that comes on here is equal to the charge that's still stored in there. That's not what balances. What's balanced is when those forces, right? The pressure, or the energy, the height of the water column is the same. And so as some of you said, yes, this is going to build up. And so when the first charge comes on there, maybe it's only 1 volt. Then the next one, 2 volts. And the next one, 3 volts. And the next one, 4. And eventually 5. But it won't go any more charge because then you would have to go to 6 volts. And 6 volts means that this guy's got to push over here. Okay? And so after a long period of time, I could say that that's charged up to 5 volts. And then again, that's what you already saw. It took less than a second for that to happen. And this is a big capacitor. Most of these capacitors, as we'll see when we do some of our electronics in class, I mean, it takes a fraction of a second. You know, we'll see, well, how long does it take? And you'll be going, it took a microsecond. It took a nanosecond. Okay? I don't think we'll do anything faster than a nanosecond. But it could be, right? It may not take long, especially if you've got these little capacitors here. Okay? And so now I've got it full. Yeah? Oh, okay, sure, yeah. He's asking if I did this. Okay, so if I did this light bulb here, really, all I've done is I already got a charged capacitor. And the light bulb will go on, but it's really getting all its stuff from here. It's just flowing like that. And this capacitor is really just kind of pointless. But pointless in far as that goes. But yes, this does have a power, and that's how then when the accident occurs and car crashes and pulls it out, we got time before the patient dies. Good. Right? Because during that time I was running off of there. So it's hooked to my circuit getting ready for that interruption. Yeah. Okay. All right. So there is some new symbolism for you, if you will. Now let's make a next step. What if I did this? What if I then take a power supply, and I'll just stick to my 5 volts, and I draw what I will call capacitor 1 and capacitor 2. Ooh. So what do I mean by that picture? Well, good. The fancy word is parallel. I'm going to use that word quite yet here, but I definitely want to do this in parallel. But let's forget the fancy words for a moment here. Could you hook this up? What does this exactly mean? Well, let me disconnect this light bulb that you asked about. Okay, and say, all right, I've got the one capacitor. What about my second capacitor? And so my second one, I'll just use this top one. Actually, maybe I'll use this one. It's a little bigger and easier to see for this big class here. But what if I hook this one up? Okay. And so my first question is, how would I hook it up? Does this picture even make any sense? Do you see the first part? So what's the next step? Yeah, so it's saying this, what I'll call the top plate of number 1 gets connected to a top plate of number 2. So if I call this the top plate of number 1, I want to hook the top plate of number 1, maybe I'll angle it that way, to the top plate of number 2. Right? And then the bottom plate to the bottom plate. Fair enough? And so maybe I should ask, does that look like that picture? Okay, good. And so that is what we call 2 capacitors in parallel. And so this is a parallel connection. Why the word parallel? Yeah, let's talk about the physics of what's going on. Look at these electrons. If I start drawing these little electrons and start making the electric field again, what happens to the first electron that comes out of my power supply? Where does it go? Okay, so maybe it jumps onto the first one, and as it jumps onto the first one, it makes an electric field inside the first one. And after it makes an electric field, it chases away an electron and finishes it. Now, what about the second electron? What does it do? Yeah, it comes off and goes, okay, we're going to get away from here. Oh, hey, look, there's somebody there. Let's go over to here. Right? And so it jumps over to the other side, makes a little electric field there, chases one away, and finishes the circuit. And then a second and a third and a fourth. And does it ever stop? Yeah, what happens here now? So eventually I'll get, say, 4 charges on here. Will I get 4 on here? Will they have the same amount of charge? Well, let me ask you this. Big tank of water again. A small, narrow tank here. And maybe another tank that's a little bit bigger. I connect them together with rubber hoses down below, and I open up the valve. Water goes to the big tank. Doesn't it start filling up both tanks? Okay. It doesn't fill all the way one up and then the other ones, right? Don't they kind of go up together? Okay. And that's what we said, right? We start putting them on both. But when does it stop filling up? When the pressures are the same. Does that mean you have the same amount of water in each tank? No. Wouldn't that depend on the diameter of it? And so I would say the same thing here. I would not say that they stop once they have the same charge. I would never say that those two capacitors have the same charge on them. They have the same voltage, right? They have the same amount of pressure, like this water tank pushing back. And so this is going to build up, and let me just represent it as being different by only putting two charges on there. But please don't ever think it's got the same amount of charges in it. That's not why it stops. It stops because as the electric field, that is the force, the analogy being the pressure, when that pressure here gets the same as these, no more will go on here. And the same thing here. And so what you're saying is the voltage is the same on this. Okay? Not necessarily the charge. So at this point, I would say this capacitor has built up a charge to 5 volts, and this one has built up a charge to 5 volts. And if I take capacitance number 1 and say it is charge 1 divided by 5 volts, and this capacitor number 2 is charge number 2 over 5 volts, you can see that they don't necessarily have the same charge. It depends on their capacitance. And so if they had the same capacitance, just like these two tanks, if these two tanks had the same diameter, then as the water flowed in, not only would they have the same height and the same pressure, but they would also have the same amount of water. But once you make one bigger than the other, they don't end up with the same water, yet they each end up at the same height. You see that? And so this is the situation you get when you have them in parallel. And you can now hopefully see the word parallel. Why the word parallel? Well, because as these electrons flow, they go either to this capacitor or to this capacitor. They have an option. It's like a freeway. You drive the freeway and you got 2 or 3 lanes. And I guess in this area of town, we've got 3 lanes. Those are 3 parallel lines, right? And if you're driving down the road towards Carp, you drive hopefully in just one of those lanes. You don't have to drive one and then the other to get to Carpinteria, right? It's one or the other. They are parallel. And that is what parallel means. They flow from one or they flow to the other, right? You have a set of parallel tracks on a train, right? The train can go this one or this one. Doesn't need to go both. Now I say all that because what if I were to hook this a little different? What if I were to hook the capacitors maybe like this? What would happen here? Okay, so some of you know it has a fancy word, series. Maybe I'll even write that down here. But I'm not worried about the fancy word, at least not yet. I mean, we have to communicate, so we have to have our fancy words here. But that's not true knowledge, right? And true knowledge is not just what the words are. But what is happening here? If you were to describe what's happening, if I were to disassemble this, and hook it up, using the same 2 capacitors, what would it look like? What is this saying? Yeah, okay, it said, okay, go ahead and take the negative. All right, so here's my power supply. Move that so you can see. Here's my power supply, and I'll start here with the negative. And it says go ahead and hook the negative to one of the plates of capacitor number 2. And so this wire right here is representing here. And then the other plate of capacitor number 2 hooks to one of the plates of capacitor number 1. So The other plate of capacitor 2 goes to one of the plates of number 2. And then what? That's kind of short. Then this first plate of number 1 goes to the power supply. Yay! Right? And so, maybe I should ask. Does that look like the picture? Right? And so I think you can see that something different is happening here than compared to here, right? And so let's talk about this one. But again, as you guys said, this is called series. Why the word series? Well, look what happens to this electron. What happens to this electron that comes out of here? Where does it go? It goes to C2. It has no parallel path. It has no option to go anywhere else. It only goes on C2. And once it gets there, what happens? Yeah, it chases an electron away from the other side. Where does it go? To C1. And then chases an electron away and finishes the circuit. But do you see how, now it's not the same electron, but do you see how this path goes here? This electron that chases away another electron, where does that electron have to go? To that other capacitor. That didn't happen here, right? It didn't go from one capacitor to another. It either went to the first one or the second one. This one that is leaving the first one has to go to the second one, has to go to the next one. It's a series, right? That's what we mean by that word, series. Our physics class is a series. You had to take physics 121 first before you could take 122. If I drive to Lake Kachuma, I got to drive the 101, get on the 150. I can't take the 101 or the 150, right? Is it 150? 154. I'm mixing my roads. Where's 150? That's the Ojai? That's Ojai Road. All right. But 154. So I've got to go one, then the other, right? And so that's what the word meant by series. Now, they have a different consequence, and that's what I'm trying to emphasize here. We talked about this one, and in the few moments we have left, let's make sure we talk about this one. What would happen here? All right, so this first one comes out. It does this. It creates a little electric field, chases one to here, makes a little electric field. Then what does the second one do? Chases one out, puts it on number 1. Number 1 goes back. Third one, chases one off, goes there, chases one back. Fourth one, goes here, chases one back, puts it here, chases one back, completes. What do you notice different here between the parallel and the series? What's the same here in the series? Right, and so in this one, I would say Q1 is equal to Q2. Whereas over here in the parallel, I was saying voltage 1 is equal to voltage 2. Okay. Now again, if an analogy helps, think about this big water tank over here again. And now I have 2 tanks, but instead of putting them side by side, I stack them on top of each other. Right? And maybe for simplicity, I'll just lay them down for a moment. If I open the valve, wouldn't the water that goes through tank number 1 be the same water that goes through tank number 2? And so whatever molecule goes through one's got to go through the other. So when something is in series like this, they're saying they have the same charge. When something is parallel, they have the same voltage. And so to emphasize that, I want to say, in the parallel case, Q1 does not equal Q2. Now, it could in the special case that they're the same capacitors. But in general, they don't have the same charge on them. They do have the same voltage. And over here, they have the same charge, but do they have the same voltage? Well, they couldn't, right? I mean, if this is C1 equals to Q over V1, and this is C2 equals to Q over V2. Again, if they have the same charge, but they have different capacitance, they can't have the same voltage. And so that's kind of our difference. We got a different scenario. We have different pros and cons depending on how we hook it up. And that's what we want to learn as we go through these chapters. Should I hook it in parallel? Should I hook it in series? What are the advantages and disadvantages? What do I get when they're in series? What do I get when they're in parallel? They have something different about them. Now, before I go too far on this, I would say there is something more to be said about these two circuits. Oh, actually, there's a lot more, but one more thing before we go. The first thing I would say is, okay, maybe I'll start here. I don't know if it's easier to see it on this one or this one. But after looking closely, I see they have the same charge but different voltage. But if this over here does have a voltage of 5 volts, like we see here, I claim there's one more piece of information I do know. And what's that? It is these two together that are pushing back against this one from coming. So what do these two voltages add up to? 5 volts. So even though they may not be equal, I do know the sum of the two voltages. Okay? I do know that they add up to. Because again, that's what voltages is. It's this energy. And the energy's got to be balanced, or the force has got to be balanced. So one more over here. Do you see the last piece of information here? Okay, we already said the voltages have to equal. We know the charges don't have to be equal. But what do I know about the charge on each of them? What does that equal? Well, you might say it is equal to the total charge that came out of that battery, right? Because for whatever electron comes out, it goes through. By the way, I didn't use these words, but did you notice that the logic behind here is based on conservation of charge? Right? This is an important point. And we're going to get to a great guy named Kirchhoff, and he gives some words to this. But it's really conservation of charge. He really is trying to say that whatever charge comes out of here, it can go here or here, but that charge has got to equal those two. And what's this really saying? This is really conservation of energy, right? This is really saying if you go for a little hike and you go downhill, uphill, and you get back where you started, don't you have to go downhill the same amount you go uphill? If you're going to get back to your car, you go down, you go up. Those are equal because you're at the same height at the end of the day. And that's a conservation of energy statement. All right, well, we'll stop there. Do more on Tuesday. Yeah.